My name is Jonathan Kane. I'll be representing the gold team. The other members on my team are Jared Baker and Emily Stark. Today I'll be talking to you about the background of our system, the theory of the experiments we went over, our first week's SSOC, the step response experiment and modeling, the frequency response modeling, the results of those, and then conclusions. Background is we are on the flow system, so it's a publicly owned treatment works sewage treatment plant. They have 3 filter presses to filter out the solid wastes. The plates are cleaned after every batch, and they have instructed us that it needs to run at about 7 to 10 pounds per minute, but our team range is actually 8 to 20 pounds per minute. This is a schematic of our system. We have the water wash inlets, flow meter to the filter nozzles, and the pump controller. And these are actually for the workers, but they shut them off for our system. And here's a block diagram where our input is the motor power in percentage to the filter wash system, and our output is wash water in pounds per minute. And the theory is the steady state operating curve. After you run your system for a while, the transients will die out, and you can get an average value for the input you put in. On the step response, you can measure the change after you change the input of your system to see how your system will respond to it. And from that information, we get the gain, dead time, and time constant, which we can put into our FOPDT first order plus dead time model to better model our system. And then also the frequency response will give us the same information, but should be a little better. This is an example of the steady state operating curve at 60% input. You can see it takes about 7 seconds for it to reach steady state. The reason for that is after the input has died away, there's water still in the system, but it drains down back to the reservoir. And so you're actually just pumping water. So it takes a minute for it to get to steady state, but you can get an average here. At 60%, we have 20 pounds per minute with an uncertainty of 1.6 pounds. After we do a variety of different inputs, we can plot them on a graph. First the output, get a steady state operating curve. You could fit a line to this and extrapolate data for different inputs if need be, or interpolate some that might be missing. In the modeling, we'll be using these modeling equations for the manipulated variable, the input. You need these variables, and also for the output, that'll be your step size, dead time, gain, and time constant. The results of the step response, here we see that the change in the manipulated variable 5%, and the change in the output 2.22%, you can get a gain from that. And finding the dead time, the time between the input change and the time that it takes your system to react. And then finding the tau, or your time constants, an example of that. Here are the results of numerous experiments we've done. You see the gain doesn't change that much, 0.07 throughout the whole thing, but it looks like a lot because of the way the graphs are spaced out. But pretty much the same. And our time delay. And then in stuff you haven't seen, this is new stuff we did the past few weeks, our FOPDT modeling. You try to fit it best you can to the system. You have your input system and model inputs, and then out here you have your outputs. You try to line them up best you can by adjusting the tau, time constants, dead time and gain, etc. Try to keep them as close as you can. We did this for all ranges, step up and step down, through the 8 through 12 pounds per minute, 12 through 16 pounds per minute, and 16 through 20 pounds per minute. You can't get them exact every time, but you get them pretty close. And from fitting it like that, we can get new values for our variables. And here's a comparison of our system model dead time. The model is pretty consistent around the same dead time. our system does change a little bit, but overall not that much. The time constant is a little better. It correlates better to the system and model, except for this right here. Not sure what happened. But let me move on to our frequency response. Every change going through a sinusoidal inputs, and you can look at how your system reacts to this input change. From this T and the period, we can get a phase shift, and then from the change in the input to the change in the output, we can get a amplitude ratio. And when we post enough of those onto a Bode plot, we can get new values for our variables used for modeling. Here the K, 0.48 pounds per minute. Go down here to the 180 phase shift, you move up to our frequency of 0.5 hertz. The order, I assumed was 1, close enough if you move this line straight up here. It was 1 over and 1 down. And then these two values right here, your tau and your time, or your dead time, you have to use the equation on this following page to calculate those. And this is the difference between the numbers for our step response, or analyzing our step response and the frequency response graphs. Dead time, almost the same. Our tau is a little off, 0.3, but it was hard fitting the model of the frequency to the Bode plot, and our gain is pretty much dead on. But here's the modeling. I was saying it's hard to fit this to it. These initial points are fitting pretty well, but down here we're getting off a little bit. It's even worse on the phase shift. Not sure if I'm doing it wrong or our values are really that off. But here on the frequency, you can see they match up pretty well going down into it. But down here, we're off. If we were to follow this all the way up, our frequency would be way off from what this is. So, other than that, I think it fits pretty well. And in conclusion, just do more experiments. You're getting more variables to model the system better. But the frequency, like I said, modeling was inconsistent, so I'm not sure if we're just doing it correctly or not.